afternoon, everyone, and I want to welcome all of you in our second session of the webinar series on cellular automata. I am very much thankful to all of you for joining us, and I really want to share that we are overwhelmed with the positive responses and encouragement we have received from the invitation. And I can take this as an opportunity to invite you for our next session also. This session is on 6th of October, where Professor Hector Zeni will deliver a talk on algorithmic information dynamics of cellular automata. In fact, he is the pioneer on this field, so it will be an interesting discussion. I want to invite all of you to join for that event also. Today we have among us Professor Dipanwita Chowdhury, Professor IIT Kharagpur, the premier and oldest IIT in India. She is the recipient of INSA Young Scientist Award, then Associate of Indian Science. She is also Indian Academy of Science. She is also Fellow of Indian National Academy of Engineers and a life member of CRSI, Cryptology Research Society of India. She has published more than 250 technical papers in the field of cellular automata, cryptography and security, error correcting code, VLSI, and embedded system. Almost all of us know her. So over to you, ma'am. Thanks for giving us an opportunity to listen to you.
Okay. Thank you, Kamalika, for your nice introduction. And thank you, Shukanto, for organizing both of you for cellular automata. Okay. So today I want to discuss or present one special type of cellular automata. Is nonlinear cellular automata, and how the cellular automata is used in cryptography for what are the properties that actually is good for cryptography, the cellular automata properties that I actually want to introduce. Okay. Probably some of you have in the meantime observed that the topic I gave is nonlinear cellular automata, and now I am telling maximum length nonlinear cellular automata, because when I was preparing, then I saw that it is actually very vast area and there are many things. So in this short time, better I focus on a very specific type, and again that very new type of cellular automata, nonlinear cellular automata, and what our experience is in the research, that this particular cellular automata is actually very well suited for cryptographic primitives as cryptographic application area. Now, again, before I start the technical things, I want to tell something. Actually, last 30 years, or even slightly more than that, I have been working in cellular automata and different application areas. There are vast application areas, and mainly that time we are working for linear cellular automata. So only last 20 years, actually, parallelly I have been working in cryptography and security also, mainly the design analysis of cryptographic algorithms. Then I saw that there are actually some properties of cellular automata that is actually very much well suited for cryptographic applications. And then last almost more than 10-15 years, this one area that I and my group members, my students, scholars, we are trying to establish these relations. So this is actually our current, or I can tell that last 20 years or 15 years, that cellular automata can be used as a better cryptographic primitive better cryptographic primitive, that means in application area. So this is one small part of that. So with this introduction, I start. first I give the introduction. I think earlier already Professor Sukanta Das has given lecture, so students must be knowing about. So I'll give a brief thing. Then what is the objective? Already I mentioned that this is the objective of this thing. Then basics of cellular, and this is the new thing I want to tell, that maximum length cellular automata and some different variants, and then how these these maximum length nonlinear, that is nonlinear cellular automata, can be used as a cryptographic application. So I start with this thing that cellular automata are good pseudo-random number generators, because always in these 1.5 hours, mainly I'll be telling cellular automata properties, but parallelly I'll try to establish that why cellular automata, why I am telling that cellular automata is a better cryptography. Okay. So this is the thing, that this is the property that pseudo-random number generators. This universally cellular automata is famous for pseudo-random number generators. Now, maximum length cellular automata, I'll be finding that maximum length cellular automata have wide range of applications in design of ciphers, error correcting codes, VLSI, then even in finite state machine testing, and many other things. Okay. So then maximum length linear cellular automata increase randomness property and provide security against different side channel attacks like power attack, timing attack. So, but linear cellular automata is known to be insecure. Although linear cellular automata is insecure, means in cryptographic point of view, because cryptography and security function we want to use that must be secure. So third party cannot get that thing. So there, although the linear thing is not secure, but nowadays there are some attacks, as I mentioned, that power attack, timing attack. All the attacks are, for these attacks, actually linear functions are more secure than nonlinear. So we cannot throw the linear cellular automata or linear functions. This is one thing. But for normal popular attacks, other than side channel, that algebraic attacks or some statistical attacks, actually nonlinear functions are essential, particularly algebraic attacks. Nonlinear functions are essential in different crypto primitives. So both cellular linear and nonlinear functions, and there, that because cellular automata has that inherent Boolean functions, so that nonlinear or linear functions, that can be actually a better crypto primitive, or that can be a good security measures for crypto systems. Now, objective already I mentioned the first in the introduction only, that exploring maximum length cellular automata. This lecture I'll be focusing on maximum length. Otherwise, in general, nonlinear cellular automata also as a better crypto primitive. Okay. Now, these I just give an introduction, very basics, because all of we know that cellular automata is a finite state deterministic machine, and this studied as a mathematical model for self-organizing and self-evolving in nature. Okay. And these uniform arrays of cells or arrays of uniform cells, if it is one dimension, where each cell has one memory, that means a D flip-flop, one memory element, and a combinational logic. So this is like this. See, this one cell consists of a combinational logic and a D flip-flop. And see, the D flip-flop means this is a memory, and this combinational logic, all of we know that combinational logic has some inputs and outputs. So these inputs are coming from the cell itself, because this and two of its neighbor. So normally if it comes, then we'll be telling the three neighborhood structure. So from left neighbor, self itself, and right neighbor. Because this right neighbor and left neighbor cell and right neighbor cell similar to this cell. That means each cell has this one combination logic design and one deep flip-flop. So it has three inputs. So this is one input left. This is one input from self. So this is self. And this is from right. So these are the three inputs. And this is the output, the combination logic output. So that actually enters into the memory. That means again, this can be, all of we know the function of the flip-flop, that this will be the next state of the memory. So this simple structure is the structure of one cell. And that's why we call typical three neighborhood cell, because left, right, and this. Now, say this is three neighborhood. So CA, three neighborhoods n cells here. So this is denoted at x0, x1 to xn minus 1. These are the states of the n cell CA. The neighborhood set of ith cell is, because it is three neighborhoods, so ith cell, this will be I minus 1, I plus 1. That means if it is xi minus 1, xi plus 1. These are the neighbor set. Number of possible binary states, because it is three, so this will be, and every state can be in two state only. Every cell can have two state, 0 or 1. So since there are three neighbors, so 2 to the power 3, that means possible binary states are 8. So here you can think as if the states of the neighbors, these three, as if these are my one table, if I think, and then this output of the ith cell gives the output, this ith cell output. Okay, so as if three input, one output. So if I frame a truth table, normal or combinational logic design truth table, then as if the truth table, that inputs are the states of the I minus 1th cell, ith cell, and I plus 1th cell, and the output of the ith cell is the output of the truth table, that function. So how this, because after that many times I will be telling function. So how these functions are, it is forming. That means every cell output I can represent as a Boolean function. For this linear function, non-linear function, I will be telling. So mainly this is the thing. Okay. So this is nothing but a truth table. If I can frame, where is I minus 1th cell, state of I minus 1th cell, ith cell, and I plus 1th cell, the current states, that will be the input, and the next state of the ith cell will be the output. So this is a three input, one output function. Now number of possible Boolean functions are 2 to the power 3. This 256. 256 such Boolean functions are possible, because binary states are 8, and again this is some 0 and 1 states. So total 2 to the power 8 is 256. So there are this type of Boolean functions. Just now I mentioned the Boolean functions, 3 input, 1 output. So that 256 such Boolean functions are possible. So state transition functions will be like that. Ith cell is xit plus 1 is f of I, xit minus xi minus 1 t, xit, xi plus 1 t. What it means? So that means, say I start at the tth state, means my current state is tth state. So current state t at time instant t. So these are my three neighbors, xi minus 1, xi, and xi plus 1, and this t represents that tth state. This is the current state. So these are my variables. What I told just now, that three inputs. So these are my three inputs. So functions are, these are three variables function, or three input function. and see the output of ith. I told the output of ith cell. So output of ith cell means it is the next state. That means if I consider the tth state, then output should be t plus 1th state. Again, you can think that because each cell has a D flip-flop. If you remember, D flip-flop means it is a memory element. So always memory means it stores some data. So that means tth state is the current state and t plus 1th state is the next state. So this is, in this way I can frame the Boolean functions. And there are 256 such Boolean functions possible. Okay. Now among these 256 Boolean functions, I'll be getting, actually these are all possible functions, all possible. So AND XOR, we know that mainly AND XOR and complement, that not and not, sorry, and or not XOR, no, or and or not. So that it will be coming. Actually AND XOR is also correct, but will be coming later. So now I am thinking only simple Queen-Matlock or Carnot map if we can use, then actually it will be of and or not functions, all possible and or not functions, and 256 such functions are there. Now that if and or is there, so we call that and or is not a linear thing. So it is not linear. We know that XOR is only linear. Now what just now I was, by mistake I was telling AND XOR. So if you have simple Boolean functions or your switching circuits and logic design or digital design you have read, now you remember that Shannon's principle that any AND OR function actually I can represent by AND XOR or OR XOR. Now see this XOR function, we call this XOR is a linear function, and this, if it is AND or OR that is there, then it is a non-linear. Now again I'll be giving more complex definition, but now linear or non-linear. Just we think y equal to fx, because this is nothing but y equal to fx type. See, this is my y and this is f of x. So y, we know that our normal, you remember your normal coordinate geometry, that y equal to fx plus c is the, or y equal to y, if it is ax plus c, x plus b. What is that equation represents? Y equal to ax or y equal to x plus b. It represents the straight line. Is it? Is it true? That straight line. That means this is a linear function. Means that y, the y directly depends on x. That in the proportion, or y depends means y varies in the proportion of x, the changes of x. We call, remember our school mathematics, we call that is a y equal to ax, or will be coming y equal to x plus c. That is a linear function. Okay, or c is a constant. Now, then what is a non-linear? Now I am not telling rule, etc. I am just giving that concept, that linear, non-linear. Now, if I consider our quadratic equation, y equal to x square plus bx plus c, or y equal to ax square. So here we know that that y, the output, it doesn't depend directly or in linear proportion or proportion linearly with the input variable. That means if y equal to fx, and fx is such that x square plus bx plus c is a quadratic equation, or some logarithmic function or exponentiation function, y equal to e to the power x. Remember, many of us or all of us, we know that how the function look like. Okay, some exponential functions. So it is not a linear. So that is the linear and non-linear concept. So now I'll be coming that. So this is again function y equal to x square plus b, bx plus c. Only difference is here it is a Boolean function. That means my variable can take only two values. In GF2, it is only two values 0 and 1. Otherwise, the concept is same. Okay. So now, so here, and again, any very simple way I can tell another thing. So y equal to ax square. Okay. This I told is a non-linear. Ax square. Ax square means a x dot x. I can tell x square. Now think instead of x dot x, I'm thinking x1 dot y1. x1 or x1 x2. Okay. Ax square, instead of x square, I'm just taking instead of one variable, x is one variable, single variable. I'm taking two variables like x1 and x2. So I'm writing a x1 into x2. So this should be a quadratic or non-linear, because I told y equal to, all of we know y equal to x square is a non-linear function. So y equal to ax1 into x2, that is also non-linear. Now here this and, all of we know that this and is actually is similar to multiplication, the Boolean multiplication, the and. That means y equal to a x1 dot x2, that will be treated as a non-linear thing. Why and is non-linear? So this way, this is the simple concept of non-linear. Okay. Since today we will be mainly discussing non-linear, that's why I'm coming from there. So just I start from my normal algebra, that y equal to x square plus bx plus c. All of we know that is a non-linear function. From there, if I jump to Boolean algebra, then Boolean algebra, Boolean variables can take only two values, 0 and 1. So y equal to, if the very Boolean variables are x1 and x2, which can take only values 0 and 1. So y equal to a x1 dot x2, and all of we know that here the multiplication and represents the multiplication. So y equal to x1 dot x2 is the non-linear function. Now again you remember your digital basics of digital circuits, that Boolean algebra. So remember that your De Morgan's law, or that if you can represent anything by and, then actually that always you can map that thing to a OR function. Okay. So in that sense, I can tell that if y equal to a x1 dot x2 is a non-linear, then y equal to b x1 plus x2, or y equal to simple x1 plus x2. Now forget about ab, because that also again will be a Boolean constant like 0 and 1. So I'm taking as a 1. So y equal to x1 plus x2, that is also non-linear. Okay. So now that means summary is and or. If in a function and or is there, then that will be non-linear. Okay. So now I'm telling these rules. These rules 60, 90, 150, these are nothing. These are actually some decimal representation of the truth table. This truth table I told. So the decimal representation of the output of the truth table. Or in other way I can tell that if I take all these functions, all possible functions, since I have 256 combinations, so 0 to 255, these are the 256. So these are decimal representation. So for every 1, 0 to 255, that actually will give you some function. So that rule 60, like 0 to 255, that we are taking as a rule. So that it is nothing. It is easy to represent some function. Because finally this is my neighborhood function, or that every CSL follows the function that is actually this rule. So rule 60, 90, 150 are linear. That means I'll be showing this 60, 90, 150. These rules are actually only consists of XORs. Okay. And 30, 50, 57 are non-linear. That means if we represent this rule as a function, then either or or AND along with XOR must be there. Because you cannot represent 30, 50, 57, all these rules with only XOR only. So these are non-linear. Now I see the functions later. So if I consider only the linear rules, there are only 8 linear rules. Why? See, these are 8 linear rules because I have 3 neighborhood functions. So see the table. I have 3 neighborhood functions. So if it doesn't depend on anyone, remember this is my y equal to fx, always I was telling. Y means my next state of the ith cell, xi t plus 1. This is equal to 0, means it doesn't depend. So this is rule 0. Now xi t plus 1 is xi plus 1t. That means it depends only on itself. See, ith cell, no, sorry. Ith cell depends on the I plus 1th cell. No, not itself. Its right cell, I plus 1th cell. That means that t plus 1th state, the ith cell depends only on the I plus 1th cell. And if I represent that thing as a Boolean function and I minimize using kernel map, actually I will be getting this function, which is rule 170. Or reverse direction, I can tell if 170 can be represented as a binary, because Boolean function can take only 0 and 1, and in reverse way you can synthesize or you use the kernel map, then actually you will be getting that xi, the function you will get is xi t plus 1 is xi plus 1t. Now if this is the rule that the cell depends only on itself, then it is rule 204. Now we see that ith cell depends on ith cell and I plus 1th cell. Ith cell means self, and this is my right cell. So self and right, it will give you rule 102. This function. This is nothing but this. If I write this function as a truth table, then the Boolean the decimal equivalent of the output of the truth table will give you the value 102. Okay. Similarly, if I take, so these are the only 8 rules that actually I can get using XOR, because self plus right, self plus left, self plus right plus left, right plus left doesn't depend on anything. Only right, only left. So these are the 8. These are the 8 rules, and this gives you the linear rules. Okay. And again, you remember these are these I am representing as one cell, ith cell. This is my ith cell, and so the figure CSL configured with rule 90 and 150. Okay. Now rule 90 and 150, we call this is the universal rules. This is called universal rules because all over world, what are the research groups they work? Mainly they work, most of the, almost 99.9 people, the CA, cellular automata researchers, they use these rules. Why? It's very nice. See, these rule 90 means the ith cell depends on its left neighbor and right neighbor. That means it is the XOR of left and right. 150 means the ith cell depends itself and left and right. See, here only the self is not there in rule 90 and it is there. So now, why it is so famous? Because mathematically it has many properties. Okay, if you know what, if you read later, you'll see. I'm telling very physically. See, why cellular automata is important, because it's a very nice mathematical structure or analytical background, as well as it is very good for VLSI implementation. Means any type of physical or hardware implementation, this is very helpful. So now see why 90 on 50 is good. Now see, for both 90 and 150 rule, always left and rights are there. So I'll fix left and right. So left and right neighborhood, always I'll fix, because in any case it will be coming. Now if it is I'll put a switch here in the cell, because in rule 90 self is absent and 150 self is there. So when the self is coming, that input I'll put a switch, and if the switch is open, that is a rule 90. If the switch is closed, that is a rule 150. So see, only putting a switch, you can actually any combination of 90, 150, you can easily implement. And that's why it is very famous, or it is very popular among the researchers, CA researchers, and to work with these things. And again, this is only I'm telling for physically, but actually it has very nice mathematical properties also. So these are called universal rules of linear rules. Now, these are important because even I'll come to nonlinear, these linear rules are important. So linear, nonlinear already I mentioned. Now uniform hybrid, probably in the meantime you know, but again I'm telling. So all these rules, if all the, say I have a 8 cell cellular automata, that means in a cellular automata there are 8 such uniform cells are arranged in one dimension fashion. That is called the 8 cells here. So if all the cell has the same rule, say if all the cells follow rule 90, then it is uniform. Or all the cells follow 150, or even all the cells follow rule 30. That means every cell, then it is uniform C. But if it is a mixed of that thing, that means the cell, actually not all the cells follow the same rules, then it is hybrid C. Okay. Now, rule vector is actually a sequence of all together with all the rules. So for example, if it is for 8 cells here, and then they are taking alternate 90, 150 rules, then the rule vector will be 90, 150, 90, 150, 90, 150, 90, 150, 90, 150. In that way, 8 sequence of 8 numbers or 8 rules. Now again, null boundary is here. That means I take now this is a 5 cell cellular automata. That means this is there are 5 cells. 5 cells, and see here this extreme left cell has some neighbor because there is no other cell here. So no other cell. So I'm taking as if 0 is coming as a left neighbor. From the left neighbor as if 0 is coming. Similarly, from the extreme right, for the extreme right cell, I'm considering 0 is coming here. So this is called null boundary. That means boundary cells, the left and right neighbors contributing zeros. Okay. So these are null boundary. And then if it is periodic boundary, though it is not there, but I'm telling, if the right cell, right neighbor of the right cell is the left cell. Just think this way. You just connect these two. These two you connect. Okay? The left and the right. That means the right neighbor of the right cell is the left cell, and the left neighbor of the left cell is the right. That means if the two boundary cells are connected, then it is called periodic boundary. And normally not much work is there, very few research work is here, because particularly for if the N is very large, that means say 128 cells, then it is a long wire to connect. That's why it is not so popular. Okay, just for research purposes, some researchers have done some mathematical things. Now we come to maximum length, because today's discussion mainly I will be focusing on here. So maximum length CA, that if an n cell CA is characterized by the presence of a cycle length 2 to the power n minus 1 with all non-zero states in state transition graph, then the CA is called a maximum length CA. See, if you think that this 5 cell, if I consider this 5 cell, and say initially, since these are memory elements, so I think that all D flip-flops has value 1. That means it will start from all 1, 1, 1, 1, 1. These are the states. Now, if I give a clock, this clock, then according to the cellular automata definition, all the cellular automata will evolve automatically. At a time, all the cell will be evolving depending on the functions associated with these things. Functions means, now we know function means nothing but the rule. That means for every cell, one rule is associated, and already I explained, rule is nothing but the decimal equivalent of the output of the truth table. That means it is a function. So this function, it will be evolving with this thing. So 1, 1, 1, 1, how many? So if it is a, that means it is a 5-bit binary number, I can think. There are 5 flip-flop means 5-bit binary number. So how many states can be there? 2 to the power 5. 2 to the power 5, 32. Now, if it is all 0, now think, if it is all 0 and if the CA is a linear CA, then actually always whatever function you use, it will be only on all 0 state only. So if I just exclude all 0 from this state, then 2 to the power n minus 1, that means 2 to the power, for this example, for n equal to 5, so this is 2 to the power 5 minus 1 means 31. 31 states will be there. Now, if my CA rule is such that if I start from a non-zero state like all 1 I told, then I just, if I continue to apply or continue to increase the clock, then actually it will evolve with all states. That means all except 0, all remaining 31 states it will be getting. Just I'll just apply clock, and then 31 I'll be getting. That means if state transition I consider with all these 31, I'll be getting only 1 cycle, and that is called the maximum length cycle. So maximum length cycle means this 2 to the power n minus 1 for n cell. For 5 cell, it will be 2 to the power 5 minus 1. Okay. So this for linear C. Now see, this is one example. This is a linear C. One rule are 150, 150, 150, 90, 90. So it will give you 131 length cycle. Okay. So this is my maximum length cycle. Okay. Now, just I'm giving just an example. So if I consider only 5 cell, if I only consider 5 cell, and say I consider only 90, 150, not much. There are 255 rules. I'm only considering the linear rules. First, I have total 255 rules. I'm considering only 8 linear rules that I have shown. Among these, I'm considering only 2 rules. The 2 universal linear rules, 90 and 150. Why I told? Now with these 2 rules only, now see, only 5 cell, only example is very small example. 5 cell and 2 rules, 90 and 150, and see I can get these 12 maximum length linear cellular automata with only 2 rules, all combination of 90 and 150. Now you think, if I consider all 8 linear rules, okay, or 7, because 1 is 0, forget. 1 is 0, so 7 linear rules, then how many such maximum length we could get? Okay, I'm giving, if some of you are interested, then you can find out that how many such maximum length linear CAs are possible. Now you think this is only 2 rules. Then I just now I am telling with 7 linear rules. Now you think, if I consider all 255 rules, 256, among these 256, forget about 0. So among these 250, with these 255 rules, what huge combinations are possible? What huge combinations are possible? Okay. Why I am telling all those things? Because now you remember, this each rule means it's one function. So this is 255. And then with this 255, remember, this will be a large number of this type of maximum cycles I will be getting. And here, this, because always I told that now onwards, that particularly this lecture, I'll try that why do we think that cellular automata can be a good function for, or good cryptographic function. So this, so here, this cryptography, just think one thing, that in security, that someone who will be the designer, I want with minimum functionalities, minimum computation will do something. But I want that attacker or the third party should not get that thing with a simple computation. Now, somehow, if you can use cellular automata in such a way, say this is what I was telling, so many functions with 255, or even these 7 rules, linear or non-linear rules, then designer knows that thing. But for one attacker who doesn't know, then for him, actually he or she has to explore all these huge search space. So that is one thing. This is one very basic why we are interested, or why last 10-15 years we are trying to apply cellular automata in cryptography. Okay, this is one. There are many other such things. As I remember, I mentioned, I started with the thing that cellular automata is a good random number generator. So that is a very basic, because all crypto primitives, whatever cryptography it is, encryption, decryption, authentication, these are actually security primitives. So all should be random. Means what? That someone cannot distinguish, or someone cannot predict. If it is a random thing, I cannot tell that what type of implementing. This is the basic thing of security. This is the basic thing. Someone cannot predict that what it is. And if the cellular automata or any random function, random function, then actually that will be a good crypto primitive. Actually, all good crypto primitives or standard primitives, standard crypto functions are actually good random functions. Okay. So now I come to maximum length non-linear. Okay, up to linear, many of us we knew. So now this is our result, and one is very nice thing that one research I want to tell, or I want to present. So this is maximum length non-linear cellular automata. Okay, maximum non-linear cellular, single non-linearity. Single non, remember this single, now you just remember. I'll be coming. Okay, so algorithm is nonlinear hybrid cellular automata. This NHCA means nonlinear hybrid cellular automata synthesis with single nonlinearity injection. That means, very simple way I am telling. Later you read. Now I just explain. I explain that with I have a linear cellular automata. Now we know. Now I have a input is an n-cell maximum length linear hybrid cellular automata. Hybrid because 9150 I have taken, but it can be many other rules. Now in one single point, in a single cell, I will put a non-linearity. Remember what is non-linearity? Simple, that AND function. I explained x1 dot x2 is a non-linear component. So I inject only one single cell, I will inject this thing, non-linearity, and the set S of contents of all cells of the LHC. So this is my input. I need one linear hybrid cellular automata, that is maximum length it will give, because if it is a maximum length linear hybrid, I need one non-linear functions that I want to inject, and then output will be a maximum length non-linear hybrid cellular. How to synthesize? That means I want to construct. Okay. So see the, I'm giving an example quickly. I just algorithm you see, and then I will explain. So this is input, that one linear function. This is my cell update functions. Cell update functions means my rules, nothing, and this rule means for every cell this will be a function. Remember, I already explained. Then this is that better you see this part. The neighbor set, Nj is the neighbor set of the jth cell. Remember 3 neighborhood cell. So j minus 1, j plus 1. So Nj is the 3 neighbor set. Now I'm giving the set, and this is the thing. So this is one function that belongs, is a subset of functions. Sorry, the Fn is the function, and these subsets I'm taking one or that gives all the states, and this is for all x belonging to x. X means my state of the cells. Okay, and this now currently I'm considering that as if this is jth cell and the cell itself and this neighboring cell. Only this thing I'm doing. This is actually I can tell only the function when it is applied on the state. State means state of a cell. This is state of a cell, that the cell state I am taking. Okay, but it depends on how many neighborhood you are taking. If it is a 3 neighborhoods, so only 3 neighbors neighboring state I am thinking. So Fn is a nonlinear function. Fn is a nonlinear function. Okay, so that means only because it is a single injection point, so only one that particular state I am applying. I'll explain with example. Now inject P, that means this nonlinear only what I told, that only one single cell I'll give a nonlinear function. So this nonlinear component rather I can take. This is a function because small things I'm telling as if nonlinear, one nonlinear component, that is a function. I'm telling P just for, this is for ease of writing, otherwise P and Fn chi is same. So P I inject into jth cell. So jth cell, the rule is Fj, means the associated function is Fj, and I XORed with that nonlinear part. See, this is my injection. What I told, that single injection, single nonlinearity injection. So this means this is the single nonlinearity injection. Single nonlinearity injection. Injected. And now apply shifting within the neighborhood. So that's why we have written P, so that you can represent this thing. Otherwise, Fn, no need of P. This is actually the nonlinear component. But you have to actually shift or distribute over the neighborhood. So that's why we have given Fi Fj plus minus 1. J plus minus 1 is nothing but the left cell and right cell for 3 neighborhood. Okay, so you got this thing. So it is shifting operation, and then inject updated P into the jth cell. This is very important. The step 7 is, you have to remember that inject updated P into the jth cell. Okay, jth cell where I actually nonlinearity I injected. So that is again you have to, this XOR operation is required. Now with algorithm later you read. Now you see that with this algorithm how it is applied. One example, then it will be clear. Okay. So I take the same 5 cell maximum length LHC. I started because this is my input. Linear CA with 9150, lot of, I have shown you one table. There are 12 such 9150 rule. We using 9150 rule, 12 such rule set I have shown, that will give you a maximum length linear hybrid cellular automata. Okay. Rule vector I have taken one such. The example is given 150, 150, 150, 90, 90. I am injecting nonlinearity in the position 2. That means second cell. Position 2. This is the position 2. So on the second cell. So injected nonlinearity function. This is now is because it is component. What I was telling nonlinear component is that x0 dot x4. Because it is AND, so that is nonlinear. So this nonlinear component x0 dot x4 that I am injecting there. So see, this is my injection point, the position 0, 1, 2. This is position 2. This is actually not second cell, I should tell third cell. So 0, 1, 2, better position 2. So here we are putting x0 dot x4. Okay. So Now see the state transition function of the cell, because remember first the linear cellular automata with rule 150, 150, 150, 90, 90. First I start with that thing. So F0 is 150. Remember what is rule 150? Self, left, right. So this is self. F0 means the X0 is the self and X1 is the right. Since extreme left cell has no left neighbor, that's why left neighbor is off here. It is only X0, X1. Okay, this is null boundary as if. So 0 is XORed with this thing. That means X0, XOR, X1. For F1, again it is 150. So F1 is X1. So X1, X0, X2, because left neighbor, right neighbor. X0 is left neighbor, X1, X2 is the right neighbor. Now F2. F2 is again 150. So X2, and now X1 is the left neighbor, X3 is the right neighbor. So it is X1, X2, X3. F3 is X2, XOR, X4. 90, because 150, 150, 150, 90, 90. So 90 is for F3, 90 means self is not there. So see X3 is not there here. X2 and X4 means left neighbor and right neighbor. Now for the right neighbor, right cell, extreme right cell, it depends only on the left because it is rule 90. So self is not there and there is no right neighbor. That means it is null boundary. So this is F4 is X3. So this is my function set associated with maximum length linear hybrid cellular. Okay. Now I apply the algorithm here. So steps 1 and 2. Remember the rule set Fn of synthesized CA n dash includes Fn. Remember that actually the algorithm that cell the rules already I got the set of functions and I that non-linear functions I'll be getting. Okay, non-linear components. So now step 3. Remember step 3 is x0 dot x4. This is it should be dot x0 dot x4. So if I or x0 x4 this is a set. This is a set. So function is x0 x4. Okay, this is the set, and this fn that it is in the neighboring set, and fn chi is the fn of this thing. This these states of the neighbors, and then x0 dot x4. So updated state transition, because in the second cell it is second cell means F2. That means actually it should be second position. That means F0, F1, F2. So only F2 will be changed. F2 is injected. So F2 will be X1, XOR X2, XOR S3. Earlier it was there. See this thing. Earlier F2 is this. F2 is this. X1, X2, X3. And now X0, X4 is XORed here. Non-linear thing, it is XORed here. So that actually has been shown in the figure. So this figure now you see that X0, X4, this is injected here. Okay. This is the cell position, it is injected here. So F2 is changed. Now this applying shifting operations. That means over the neighborhood state. That means, or you can think, this is very common thing, as if you evolve the neighboring states. Why I'm telling it is distributed or shifted over neighboring states? Because it only will affect the all the cells that depend on the X2. Only because F2 is changed, that means the states or the cells that depends, a state of the cells that depend on X2 only, that will be changed only. So that's why we call this is distributed or shifted over neighborhood. So now see, because it is 2 and it is 3 neighborhood, so F0 will not be affected because it is 2 cell before, 2 cell left. It is 2 cell left. So it is not in 3 neighborhood structure. So F0 is simply what earlier it was there, rule 150, X0, XOR, X1. But F1 is its just left neighbor. So it will be changed. So F1 earlier it was x0, x1, x2, 150, and now this, which was injected in only second position, now it is actually affecting, or it is actually non-linearity is induced. Non-linearity is induced in the left neighbor. F2 is already injected, this is injected, and this is induced. F2 I have injected. Now again F3 is in 3 neighbor. So F3 will be earlier x2, x4, and this is because it was rule 90. So only it was x2, x4. And now it is injected. This is induced. This is injected here, that is induced. So for F1 and F3, these are non-linearity induced, and for F2, this is injected. Similarly, for F4, there is no effect because F0 and F4, they are not in the neighborhood of F2 or X2. So that's why F4 equal to X3, it remains. Okay? I think it is clear. Is there any question here? You remember, later you ask. Okay? Because this part is slightly, you have to remember. Okay? Now, ensure maximum periodicity. Now see this, I told you step 7. Step 7, again I have to, this injecting part, that actually I have to again XOR. So this is one, just we can think in 2 different way, that as if we needs to be injected to the same injection position 2, because it is I injected in F2. So F2 is F2 XOR x0 XOR x1 dot x3. Actually, it comes with some very analytical property from this thing, the rules of all the states. So these x0 XOR x1 dot x3, it will be coming from there. So it is here. Now the state 8 state transition becomes, now if you do with this thing, state transition becomes, already I explained x0. F0 is this, F1 becomes this, F2 is, now see F2 becomes this x0 x4 as well as that step 7, this x0 XOR x1 dot x3, it is coming, that another nonlinear component, it is coming from there, F3 is there, F4 is x3. So these are the, it is coming like now as if, see, as I injected here only one, earlier I have shown, now as if another non-linearity components have been injected here, as if the effect is like that. So now it is already proved. I'm not showing here, it is the proof that it will give you the maximum length non-linear hybrid cellular automata. So this is one type of construction, and that it will give you the non-linear hybrid construction. That means it is starting from a linear, maximum length linear hybrid cellular automata, injecting in a single, remember, in a single cell, some non-linearity component. Non-linearity means only 2 input AND gate. 2 input AND you have injected, and finally you are getting this maximum length non-linear thing. Now I should come the cryptographic properties of the synthesized NHC. Okay. Here actually with this short thing, again I should not tell the cryptography, but as I already mentioned, these are actually, I'm only showing 3 very basic properties that to be maintained for a good cryptographic function. One is called non-linearity, one is called balancedness, one is called correlation immunity. Okay. So in the, I just show the definition. Okay. I thought that it will be needed. Okay. Okay. You can see this thing, non-linearity. Hello.
Yes, ma'am.
So just see, I'm giving, this is basic definition. The minimum of the Hamming distance between a Boolean function f and all affine functions involving the input variables is known as the non-linearity. Because already I mentioned the basic from the where the concept of non-linearity coming. But this is, I thought that I must say the actual definition. So affine function is a Boolean function expressed as XOR, sum or all of its input variables. Simple XOR function is the affine function. So example is, say if I take is a, here plus is XOR. Okay. So this is a 4 variable function, it's XOR, it is affine. But see, if I just introduce AND, this is not affine. Okay. And this affine, so I've given the definition, the minimum of the Hamming distance between a Boolean function f and affine functions involving the input variable is known as the non-linearity of the functions. Just what in the beginning I told, AND or, actually this is nothing but this thing, that any AND you have included, or instead of AND I could give OR. This a plus is XOR, so I could give OR, then also it becomes a non-linearity, and this is non-linearity. Then balancedness. Again, balancedness, very simple way I can tell that if you take a pattern and you see the number of zeros and number of ones are same. Okay. I can tell this is a balanced. Now you will be telling, what is this pattern? So I'm telling this pattern is as if these are my outputs, a single output function. And if I take all possible inputs, these are outputs. And then if you see the function is such that it is a number of inputs and the number of zeros and number of ones are same. Just you think 2 input XOR. Simple 2 input XOR. All of we know that 0, 0, 0, 1, 1, 0 and 0, 1, 1 and 1, 0, 1. This is the truth table of the Boolean function. Truth table of a XOR, 2 input XOR. So that means you see that if you write this in a truth table, that 0, 0 and 1, 1, these 2 inputs, it is giving you 0, and 0, 1 and 1, 0, it is giving 1. So that means number of zeros and number of ones are same. So this is balanced. So XOR is a balanced function. Okay. Now, if you take AND or OR, now you think AND OR is not balanced, because that's why this is another thing why XOR is so important in cryptography. Okay. So Boolean function of n variable is called a balanced if it is Hamming weight is exactly 2 to the power n-1. This is the actual technical definition I thought I should tell, because everything I'm telling from basic. And so this is balanced, but and is not balanced, because only for 1, 1 it gives 1, remaining all 3, 0. Similarly for OR, you will be getting 3 cases 1 and only 1 case is 0. So these are not balanced. Okay. Similarly, the correlation immunity. This is again one. Again this can be, I can tell what I told you. It will be very good. It is secure if I cannot predict. If I cannot predict beforehand, this is the thing, then it is very secure. One message I am sending to you, if someone cannot predict, then it is very secure. This is the basic thing I can think. Then that means what? That means I don't get any relation. So that means if I have beforehand many functions are there and I cannot get any correlation between them, so that means that should be secure. So that is called correlation immune. Just from common sense I am telling. But this is a Boolean function of n variable of tth order is correlation immune. If t belongs to 1 to n of size t, the probability distribution of its output is unaltered. That means what? It is not biased. Okay? It is not biased. And then you can tell this is, and the largest possible value of t is called the correlation immunity of it. That means the maximum, the cardinality is t, and the maximum value of t you will be getting, then it is called the correlation immunity. There are many other properties, but these 3 are the basic crypto properties. These 3 are the basic crypto properties. From there, actually, you can get many other crypto properties, which are actually will be very good. So now I come to that point. Now it will be clear. So NHC is synthesized from LHC of rule vector this. Just now I have shown that with this rule set, I have synthesized, I have constructed one nonlinear hybrid cellular automata. Now the state transition functions remains balanced. Now these are the some result I am showing. This is actually some with many states rules. We have done some statistical things, and just I am showing the result. This is the nonlinearity, unbalancedness, and correlation immunity, because these are the three basic crypto properties must be maintained by any crypto functions. And if I just run 8 iteration we give, then these are some nonlinearity values. Actually, this is the Hamming distance between this, so you can compute these values, and we see that these are the values we get. Okay, this nonlinearity. Balancedness is, I'm telling true means it is actually satisfying this property, that 2 to the power n minus 1 what I told. This is actually balanced. And similarly, some correlation immunity that I can compute, and we have given that this is my correlation immunity is this. Okay, remember. So these are the taking this synthesized nonlinear hybrid cellular automata maximum length, that the crypto properties we have found that it is good. Now what we have done is maximum length nonlinear cellular automata with multiple nonlinearity injection. So we thought, see, from common sense, first we have injected in only one cell nonlinearity. Now common sense tells that if the function is overall function is more nonlinear, then it should be more secure. So from cryptographic point of view, so we first tried to do that thing. So what we have done, that's with same construction, not only one single point. Remember this multiple nonlinearity. That means in multiple cells we have injected. So obviously more cost will be required. Here more cost. Okay, remember. But at the cost of hardware, because nonlinearity more means actually more AND gate, 2 input AND gate. If it is 2 input AND gate, see here I have taken only 2 input AND gate. So again another 2 input AND gate we have to take. Or if I want to inject in 3 places, 3 cells, then it will be 3 places I have to put. So it will be more costly, but more nonlinearity I am injecting. That means here actually always it is the thing that you have to compromise one thing, either some property or what you want to achieve, that property you get at the cost of something. So this is at the cost of hardware or at the cost of AND gates you are getting. So the same algorithm, so I'm not explaining the same thing, only difference is, and one thing, another important point you remember here, the condition is given that some condition you have to maintain, that here following 2 criteria here, that there must be some distance, there's some distance to be maintained between the 2 cells where the injection the nonlinearity injections we are making. So there these 2 criteria we have to maintain. Okay, otherwise it is the same algorithm we can do, and this is again same examples, only here we have taken 9 cell because multiple point I have to select. So within 5, if I take only 5, that condition I cannot maintain this condition, because that it should be minimum 3 cells in between them. The 2 cells where I want to inject the nonlinearity, there must be 3 cells in between. So we have taken 9 cells, and this is again linear hybrid cellular automata, because that is universal using rule 9150. This is now, see, nonlinearity injected positions is 2 and 6. That means difference is 4. So that condition is satisfied. Okay, the minimum 3 cells in between. 4, 3, 3, 4, 5. Minimum 3 cells. Now again we have these are the 2 points. See, this is the cost. Earlier I have only 1 input AND gate. Now it is 2 input. This AND means this is 1 AND gate is required. So that functions we have given. And now the similar way, totally the similar. These are my linear functions initially for linear hybrid cellular automata. Now with the 2 and 6, I have injected 2 and 6, we have injected and spreaded. These things are there, and then we'll be getting another thing. Now, why? You will be thinking, why again we are doing? Because that is the experiment we want to do, because intuitively it thinks that more nonlinear means it will give more security. But I cannot tell in qualitatively, because you have to prove that thing. Or so the 3 crypto properties that we have earlier we have seen. Now again we have done the experiment, because forget this is think that this some linear hybrid cellular automata I have taken. This part I didn't tell with polynomial, some taken, and these are the positions where we have actually non-linearity we have injected. Okay, and then the non-linearity with iterations. What we have done, we have many iterations we have given, that seven iterations, and see how the non-linearity is increasing. It's a tremendous increase. See the multiple, because at the cost of this AND gate, we are getting so much non-linearity here. Earlier you have seen that for 5 number you have received, it was non-linear, but not that type of value we get. Okay, for 8 maximum, 12 we got maximum. That is also 5 variable. But see here, it is a tremendous value we are getting. Okay, see that thing 19. If we just iterations we are giving, and we are getting so much nonlinear values. Now comparison with rule 30. Because if some of you work in cellular automata, you know rule 30 is very famous, because the Wolfram, who is the father of cellular automata, so he only proposed that nonlinear cellular automata can be good for cryptography. He actually proposed long back, and he used rule 30. He proposed that rule 30 can be explored. Although later rule 30 was seen as the weak, is vulnerable, it is attacked. But he only told that nonlinear CA can be a good choice for cryptography primitives, he told. So that's why, but later, initially he gave one construction and one application, but later this rule 30 was broken. That means it is attacked. So now what we have shown, that comparison with rule 30, because rule 30 is the, again, since it is proposed by Wolfram, that is taken as the standard nonlinear rule. So we have compared with rule 30 cellular automata. So nonlinearity of maximum length, synthesized NHCA increases very fast with iterations. Okay, that we have seen. And what we have seen, the all crypto properties actually much better than rule 30 CA. So that comparison we have done, because as already I mentioned that rule 30 was the standard in nonlinear rule, because Wolfram proposed that thing. And you see that here for rule 30 CA, this thing we are getting. Nonlinearity is for iteration 1, 2, 4, 36, and it is not maximum length also. And here synthesized NHCA with single nonlinearity injection, we are getting 16, 64, 512. With rule 30, we are getting 36. Here with maximum length CA, we are getting 512. And see synthesized nonlinearity with multiple nonlinearity, we are getting, here it is for iteration 1, it is same. Because remember the way we have constructed, for iteration 1, it is of no difference. So that's why iteration 1, it is same. Okay. And then iteration 2, immediately it is iteration 2 means that nonlinearity is getting induced. So if it is single point injection, the iteration 2, it is 64. But it is a 2-point injection, it is just jumped to 256. And again now it is here 2048. Here it is 512, it is 2048. So it is, and we are getting maximum length also. So this see the how the crypto properties, we are getting so nice crypto properties with this maximum length nonlinear cellular automata. Okay. So these actually I want to mention now, that why this maximum length cellular automata is a better crypto primitive. I told that was my topic. Okay. I think I slightly I can establish that this thing, only 3 basic crypto properties I have established that. So summary is that studied nonlinear rules of maximum length nonlinear cellular automata with single nonlinearity, then with single or with multiple nonlinearity, okay, and then these maximum length cellular automata multiple nonlinearity injections are better crypto primitive with respect to the security features. And there are many other crypto properties, but just as the basic idea, because that 3 are basic, others are actually you can compute from there. So these are the things that I think some questions, and if you have any doubt, because I told probably very fast. So questions, okay.
Thank you so much, ma'am, for the interesting topic. Yeah, you are expecting some questions. I would request whoever is questioning, putting some questions, to please turn on your video and then know you. Yeah, Sumit.
I have a question, madam.
Hello. You are? What is your name? Your name?
Sumit Adok. Sumit Adok.
Okay, okay, Sumit. Okay, now I can go there. Okay, I can see that thing. Please ask them.
Actually, madam, my question is, can we get the nonlinear rules? That means when we inject a single nonlinearity, like for those examples, 5150, 90, 90, in the second position, we have inject some nonlinear function. Can we get back the rules?
Not
produce the rules.
Sumit, please again, because it was dropped. That in the meantime, please repeat your question. Repeat your question.
Hello. Is it okay?
Please repeat your question.
My question is, suppose that 150, 150, 150, 90, 90. This is a 5-cell linear maximal length here. The second, you have in the nonlinearity. That means nonlinearity.
Okay. Hello. I'm requesting others to please put off your video or audio. Audio also you please put off. Otherwise, there's disturbance. Put off your audio. Please put off your audio. Kamalika, you can announce that. Otherwise, I'm not getting his question.
Yeah, anyone is unmuted. Have anyone unmuted yourself? I don't see actually. I don't see anyone who is unmuted. Maybe Sumit is having background noise. I don't know.
Sumit, tell Sumit. Oh, Sumit's.
Hello, madam.
Hello. Sumit.
Is it okay?
It is okay. I am also. I put up my video also. Okay, you tell.
Okay. Actually, my question is, when we inject the nonlinearity second position, so, is this possible to get back the nonlinear rules? That means the rule is we can replace the rule 150 like a nonlinear rule 86, 89. Is it possible to produce the rules?
Oh, it's a good question, Shumit. No. See, the difference is when that nonlinear rules or linear rules we tell, we actually tell that rule with respect to 3 neighborhood. Remember that 255 rules I told because I considered 3 neighborhoods here. Okay. Now the way we are constructing, now it is getting spread into 5 neighborhoods. No, because
5 neighborhood. Okay.
So the rules you will be getting, but that will be again you have to consider the 5 neighborhoods here rule. That's 5 neighborhoods here, not the 3 neighborhoods here. No. Did you get? Because
yes, madam. Yes.
then you will be getting, you must be getting the rules, but that rule should be, you have to give the decimal value when as if it is a 5 neighborhood nonlinear C. You must be getting, okay, but this is the value will be different, because that time it will be not 2 to the power 8, it will be actually 2 to the power 32, because for
2 to the power 32.
because 2 to the power 2 to the power 3 for 3 neighborhood, this time it will be 5 neighborhood, so 2 to the power 2 to the power 5, and then you will be getting the value. Yes. Good question. Yes.
Thank you, madam.
Any other thing?
Yeah, I want
So
to
just
ask
one
one
point.
thing. Okay, sir.
Monica, okay. So in the algorithm, this is very nice algorithm, especially injective single nonlinearity. So in step 7, you said after doing some shift operation and some assignment, it ensured that you'll get the maximal and same. The maximality is ensured.
Yes, actually
I'm interested in the proof of this. Because when I'm using some rule, the 9150, the sequence is no more there. Still, I'm getting maximality. So, is there any proof?
Yes, proof is there. Yes, proof is there. So actually, that I think it is 4 years before, probably in one cellular automata conference or Act3 or automata conference. Actually, we that time we could not prove this thing. So now Shopon, just one PhD scholar, actually he has proved this thing, and it can be. So if you are interested, I can send you the proof.
Oh yeah.
Now it is only his PhD, and he has proved. And he actually earlier Shamit Ghoshi proposed that thing, only the non-linearity. There we could not actually, it was not proved, but we got by simulation we got the maximum length. Now Shopon in his PhD, he has proved now with single injection, as well as he only proposed that multiple injection, because multiple injection, you have seen the property is actually jumping. Crypto properties actually it is it's very nice crypto properties we are getting, and actually we are now other crypto primitives we are applying this way. Okay, now yes.
And I believe the complexity of this algorithm, is it polynomial or complexity of the algorithm?
Complexity is polynomial, because see, finally to that the novelty of CA, or that thing we are using, because you are only injecting 1 and 2 input and get, or even 2 or 3 input and get, but finally the clock, this is the thing. And since why I'm telling polynomial time, because it depends on the n-cell CA, and maximum length is 2 to the power n minus 1. So proof, yes, we can do that. So it is easy. So that's a very nice thing actually. We can do.
Thank you.
Actually, many things are there. I tried to give the overview, and actually some analytical background is there that I tried to omit that part.
Okay.
But it is available in the paper. One paper.
Is the proof published or no?
No, proof is not published probably. Okay. Proof we have sent, just communicated. Okay. But I can send you that. No, it is not.
Thank you.
Okay. Okay. So, Kamalika. So you have any question, Kamalika?
Yeah, I wanted to ask you almost the same thing that Sir asked. So one more thing, ma'am, you said that there will be some distance that is to be maintained between the 2 points of injectivity.
Yes, actually that is also, that comes under the proof. Good question. Actually we have, since the proof is big, I omitted. So that's why the condition I told, because I should tell honestly, that is the condition. And you will understand this thing. Otherwise what will happen, unless this in between these three cells we cannot put, then the way we are getting the rules, actually I cannot tell this rule is, since we see, remember we have induced and three neighborhood thing we have considered. So minimum three cells I have to keep here. See,
yeah, to make a gap between the
yes, second position, that means fourth is the neighborhood, and sixth position, so fifth is the neighborhood, and I have induced one, so another, so that actually it should 3 and 4, one should be then only, so it actually comes on part of the proof. So that position is to be maintained. Otherwise, we saw that the way we have synthesized, it doesn't work. Because it actually it is clear that it will not work. We cannot get that.
Okay. So although it is, we were started with 3 neighborhoods, but the actual thing will be lifted over 5 neighborhoods. But the design will be based on the 5 neighborhoods.
Actually, we are starting with 3 neighborhoods, but it is, and that is also very important from cryptography. We call it is diffusion. Means it should be spreaded, and that is our designer's point of view. Always that we need. So from 3 neighborhood, it is getting 5 neighborhood, and in this way it is diffused. So that is also one very good, nice property of that we can employ in cryptography. So that's why we are, as I told initially, that many years we are exploring this thing.
Okay, thank you.
Okay.
Any other questions?
Yeah, I have a question. Hello, ma'am. My name is Chowdhury.
Yes.
Ma'am, when one rule was injected to a CA, it was secured because of because we are getting maximum length CA. So, ma'am, could it be broken? I mean, you have later injected 2 rules to the CA. So, as Rule 30 was broken previously, and then you tried to inject a non-linearity to the CA, then I mean, is injection of 2 rules more, I know injection of 2 rules to a CA is more secure than injection of
Yes,
1 rule.
Obviously.
But can anyone break this CA?
Yes. Normally, because see today what is secure, even after 5 years it can be insecure, it can be broken. So I cannot tell ki it cannot, because there are many new attacks. Normally it is evolved. So now when we tell that secure, it is secure, that's the 3 very basic properties I have shown. Okay. Another thing is, so now I'm telling with these basic properties it is giving. That's why I told these are the properties. See, these are how these properties are nice. But thing is that when we actually this function we employ in some cryptographic applications, not as it is we apply here. Okay. So and not see here only seven iterations or 8 iterations. It may happen that some more iterations I will run. And you understand, if more iterations, then obviously the function become very complex, and then it is very difficult. So that is what I told, that very basic function. But when actually it will be employed in cryptographic applications, then it is up to the designer how he will be using this thing. And in that, his task, actually designer's task is to use in such a way, or is to frame the application where this, that's why I'm telling crypto primitive, because these are the basic functions that you can use. Okay. So that is his task. Yes, that's why I told I didn't go to any attack, etc. I told 3 basic properties that are very good, because that should be the pillar. Okay.
Thank you, ma'am.
Okay, any other question? We can take one more
Yes,
question.
I have a question. Ma'am, this is Shukanna Mukherjee. Ma'am, actually what you explained, from that we can understand if we try to inject the non-linearity function, it results ultimately 5 neighborhoods here.
Yes.
Okay. Ma'am, can we apply three neighborhood CA just by injecting a nonlinear rule which will be applicable in case of cryptography. That means what I try to say, can we apply nonlinear
yes, I got. You are telling that whether simple nonlinear three neighborhood C
yes, yes,
we can apply.
yes.
Yes. See, rule 30 is a three neighborhood nonlinear C. Rule 30. Okay. Rule 30 is a three neighborhood nonlinear C. And there are many that we have earlier we did, as I was telling, many years I'm working. So for this maximum length, we have also done some work. We designed some crypto application, some cipher we have designed where we can use actually all these linear, non-linear, neighborhood non-linear. Yes, you can do that thing. You can do that thing, and then
Okay.
you have to compare. Here, what
Okay.
I have tried, I have tried to show you that the basic properties are very nice here. That you have seen, no, that it is actually the properties are jumping, na. So that may not be so good because
Okay.
because if it is three neighborhood, as I mentioned you, this is one thing in cryptography. This is another thing, that how it is diffused, how early, how quickly it affects others. Okay.
Okay, yes, ma'am, got it, got it. So the one another question, therefore, so instead of 5 neighborhood, if we extend to 7 neighborhood or just we increase the neighborhood, so will it be good for cryptography?
It will be very it will be good, obviously, but the main problem is that cost will be very big, cost will be more, and that time it may happen that we cannot tell this is a cellular automata, because cellular automata is that neighborhood should be there. So if I think say at 15 cells or 10 cells, then I cannot tell that this is a 10 neighborhood CA. Okay.
Okay, ma'am. So just one question, another question, ma'am. So should it be restricted to 5 or it is kind of optimization?
No, I'm telling. See, I have started with 3. In the process, it is coming with 5. But I have not done that thing. I started with a 3 neighborhood non-linear hybrid cellular automata. Remember?
Okay.
But that is, don't be confused. I have not used any 5 neighborhood cellular automata. I have not used.
Yes.
I have done 3 neighborhood, and I have injecting a nonlinearity in the process. That means when I that say cellular automata evolves, automatically it was getting nonlinearity with 5 neighborhood, 7 neighborhood, like that. And, and just think, your linear cellular automata also it happens. Remember that 3 neighborhood CA, when you just more clock you apply, then actually that neighborhood increases. It also happens the same thing. Here, nothing great here. Only is the linearity and non-linearity. And you can think overall in this way, the function is getting very complex, so it is very difficult to break.
Yes. Okay.
And
Thank you, ma'am.
Got
it.
Okay, thank you so much.
Okay, Kamalika, thank you for inviting.
For joining us and having this much of interaction.
Okay.
Okay, and I want to invite all of you for our next session also. So, thank you so much, ma'am.